Okay, good morning. So first thing I want to remind is that we're going to have another test on Thursday, next Thursday. So so I try to remind you at the beginning of every class. Uh, and also I'm gonna send you the reminder at the very just a day before the test. I'm gonna send you another reminder. So make sure you don't miss it. I think the test format is going to be the same as the first one. We're going to have some multiple choice problems, and then we have some questions. Okay, let's back to um, the topics of paging. So we start the topic of paging last time. Um, we mentioned that in early computer system, we used to allocate each program into a consecutive memory space, which means that for each program, depend on the size of the program, we need to allocate the corresponding memory space, physical memory space of the same size or bigger to accommodate that program. Now, so if we could not find any chunk of memory space which are not big enough for the program, then the program has to be waiting. Or we have to use the swapping to swap some of the program in the memory out of the memory and then free up some of the memory space. So then we hopefully we can get a memory space which is big enough for the program. So we can load the program into the memory. So this is not a very efficient memory allocation. Um, Remember, we have one of the rule called the 50% rule. That means for this kind of memory allocation, there's always 50% rule applies. That means with the fixed size of memory space, only 2/3 of memory going to be pretty much loaded with the program, and the 1/3 of the memory going to be empty. So the reason for this is because with the memory location, with the memory allocation, you expect to see a, whole bunch of programs scattered all over the place, and also a whole bunch of holes in between. When I say hole, that means the free memory space. So that's the situation with the consecutive memory allocation. So people start to actually figure out a way to improve the memory utilization. One of the approach is to use the paging. Use the paging. Now, in paging, so each of the physical memory space is divided into a small unit, into small units, and that small unit it's these units are all of the same size, and these units are called page. Okay. Now here's the example. Suppose I have logical address using 5 bits. Now with 5 bits, so how many logical memory address I can represent with 5 bits? We have a very easy formula for this, right? So because we're supposed to use binary numbers, so that means, you know, each for 5 bits we can represent 2 to the 5, which is 32 logical address, logical addresses, right? So that's the total size of the logical addresses. Okay. Now with paging, we're going to divide these 32 logical addresses into small units. Now, how big is the size for each unit? It's up to the designer of the program operating system. Actually, it's not actually up to the designer of the operating system. It's actually up to the designer of the physical memory. Okay, so when you the paging is actually, the concept of paging is actually built into the hardware into the physical memory. So when you actually create a memory, then you already structure the memory in terms of the page size. So suppose that if we say, well, if we divide 32 logical addresses into 4 pages, suppose I want to, divide the total of 32 logic addresses into 4 pages, then what's the size of each page? So we have a total of 32 logic addresses. And 32 going to be divided into 4 pages. 32 divided by 4, we got an 8. So that means each page that contains total of 8 addresses, right? So this is actually displayed over here, like this case. So you have a 5 bits, so with total of 32 memory, the logic addresses. And if we divide it into 4, if we actually, divide these total logic address into 4 pages, and the size of each page is 8 addresses. Okay. So so in this particular case, so how are you going to actually, represent this mechanism? So in this case, the 5 bits are basically divided into 2 parts. Okay. The first part, because we only actually requires 4 pages, right? So that means 4 pages, and how many bits do we need to represent 4 pages?
Two.
We just need 2 bits, right? We need 2 bits to represent 4 pages. So that's why in the logic address scheme, when we divide these 5 bits into 2 parts, then we use these 2 parts to represent the page numbers. Okay, because 4 pages, then you can represent page number 0, 1, 2, 3. So that's, and then this part is used to represent something called offset. Okay. Now remember, for each page, like this one, page 0, the offset starts from 0, 0, 0. So that's the first, represent the first memory address in this page 0. So the offset starts from 0, 0, and always end with 1, 1, 1. Because with 4 pages, now each page size is 8 bit. No, I'm sorry, 8 addresses. 8 address requires 3 bits. Okay, so for these 3 bits, the first address offset value is 0, and last one is 111, which is actually 7. So we start from 0 to 7. Now same thing with the second page, page 1. The first actually 2 bits represent the page number 0, 1. And then this is actually the offset, start from 0, 0, 0 and end with 1, 1, 1. That's always the scenario. That's one of the configuration. Okay, in another configuration, Now, if we say, well, I want to, configure the 4 bits in another kind of configuration that I try to actually divide these 32 logic address into 8 pages. Okay. So if I want to divide it into 8 pages, now the total memory, logical memory address is still 32. But now if we want to divide it into 8 pages, then the page size is going to be smaller, right? Now what's the page size? It's 32 divided by 8, which is 4, like this case. Okay. So now, so in this case, with total number of 8 pages, then we need 3 bits to represent the page number, and the size of the page is reduced from 8 to 4 now. So we actually pretty much switch this size. Now the number of pages increased, but the offset is decreased. That makes sense, right? Because overall, the number of pages times multiplies the size of each page is actually the total memory, total logic address space, right? The total logic space, which is 32, equals the number of pages times the size of each page. So if the number of pages is 8, the size of page should be 4, because 8 times 4 is 32. Now, if the number of pages is 4, so I decrease the number of pages, then each page is going to be bigger, right? So it's kind of like the numbers, between the page size and also the number of pages. So that number is actually, if one is bigger, increase the other one going to be actually smaller. So that's the trade-off. Okay. So if I use this scheme, then we have a total of 8 pages, and each page has a size 4. And the offset basically has actually 2 bits. Now the offset basically going to start from 0, 0 to 1, 1. Another page offset start from 0, 0 to 1, 1. Okay. Now basically the offset, for example, like a 1, 0, it actually measures the distance of this memory address to the beginning of the page, right? So offset 2 basically means, okay, this is actually, it's third address in this page, because the first one is 0, the second one is 1, and third one is 2. Okay, so that measures the relative location of this address to the beginning of this page. So that's the offset. Okay. Now with this, then we can use the scheme in our memory management. So now let's say the logic address is here. Okay, it's actually 5 bits, and I use total of 8 pages. So I use 3 bits to represent the page number, right? And 2 bits for the offset. Okay, so the total number is 32 with 5 bits logic address. Total number is 32 logic addresses. Now, for the physical memory, if the physical memory is 6-bit, that means the physical memory is larger than the logic address, right? With 6 bits, I can represent a total of 2 to the 6, which is 64 physical address. Okay. Now, with this page scheme, if I use a page, so the page size is 4 addresses. So remember, in the paging, when we actually choose the page size of 4 in the logical address, then we have to choose the frame size, also choose the frame size 4 for the physical address. Because eventually, we're going to actually load each of the page into each of the frame. So the size of the page should be the same as size of frame. Now with 64-bit physical memory, if the page size is 4, 64 divided by 4, we got 16. So we have a total of 16 frames. Okay. Now with this, we can map each of the page in the logic address into the physical memory location, because the page size and the frame size are the same. So now the next question is, suppose I have a program here, and my program is eventually divided into the pages. Okay. So when I measure the program size, I'm not going to measure how many memory space I'm going to use for the program. I just measure how many pages I need for that program. So then I can actually say, okay, so this is the program I have, and the page 0 for the program, here's the page 1 for the program, and page 2 for the program, and here's page 7 for the program. Okay. Now, when I try to execute the program, so I needed to load each of the pages into the physical memory. Actually, I need to load each of the page into the physical frame. Okay, in the physical memory. Now, suppose I load page 0 into frame number 1. Okay, here I load into frame number 1, and I load page 1 into frame number 3. Okay, page 2, I can load page 2 into frame number 2. Okay. So remember, when you actually load each of the page into the frame, we don't have to load into the frame in certain kind of order, like a consecutive order. You don't have to do that, because if I say I have a program of 4 pages, so that's the size of my program. My program takes total of 4 pages. Now, all I need to know is, do I have 4 frames in the physical memory, right? If I have 4 frames in the physical memory, then I can load these 4 pages into the memory. It doesn't matter where are each of these, where's each of these frame. These frame could be separated. Okay. And also, when I load page 0 into a frame, page 1 into another frame, so the order of frame is not really matters. Okay. So for example, like in this case, I can load page 1 into frame number 3 and page 2 into frame number 2. So it's just opposite order. It's okay. Now the only thing we need to know is the memory management need to record which page is loaded into which frame. That's important. Okay, which page is loaded into which frame. Okay, now that's called a page table. So we build a page table. The page table should record which page loaded into which frame. Okay, that's the page table. Now, in this particular case, the same case, we can say, okay, so page 0, 0, 0, 0, map to friend number 1, right? Which is actually 0, 0, 0, 1. So the friend number 1. Now page 1, suppose I load page 1 into friend number 3. Okay. And then I can replace this number, page 1, 0, 0, 1, into friend number 3, which is, remember, friend actually use 4 bits because the physical memory size is 6 bits, and I only use 2 bits for the offset. So I have a 4 bits for the friend size. So that means 001 maps to 0011, which is actually 2. Okay. And the page 2, 010, that's 2, right? So that's 0, that's 1, that's 2 in terms of decimal value, and that's 3. Okay. So page number 2, 010, which is this, maps to friend number 2. Okay, so the friend number 2 is 0, 0, 1, 0, right? And the page 4 maps to the last one, friend number 15. Friend number 15 is 1111. So page 4 is actually mapped to 1111. Okay, I'm sorry, page 3 is mapped to 1111. It's actually 15. And the next one, I don't know. Once we actually know exactly which page, like a page 4, maps to which friend, then I can just fill out these corresponding friend number into the page table. So the page table basically tells you which page maps to which friend. Okay. Now the next thing we need to figure out is, now if the computer actually start to execute the program, okay, when computer start to execute the program, the computer gonna actually start, for example, from the first memory address. Okay, so that's the entry point. It's a main, for example, it's a main function. Okay, main method. So if the computer start from here, then so the first instruction is located in the logical memory 00000. And then the CPU, when CPU try to fetch the instruction, CPU is not going to actually fetch the logical address, right? Because logical address is imaginary memory address, because the actual instruction is loaded into the physical memory address. And where is the physical memory address for this 000? And then we need to look at the page table. Say, okay, 00000, what is this memory address located at? What is this? What is this address located at? Or I can say which page number, which page this address is located at. And then I find out, oh, that's page 0. Okay, look at page 0. What's the corresponding friend number? It's a 00001. Okay, so I know it's in friend 00001. Okay, now the next thing I want to figure out is what's the corresponding physical address? And then I look at the offset. The page is 0. Okay, so I map to friend number 1. No problem. Now, the offset is 0, 0. So I look at this offset. So it's also 0, 0. So that's the first address in friend number 1. So what is the physical address correspond to 0, 0? The physical address correspond to 0, 0 is, first I find the logical address, which is 0001, right? 0001. And the offset, well, I copy the offset because the offset is never going to change. So So the physical logical address 00000 maps to physical address 0000100. Okay, so now the computer CPU going to find out, okay, so that's the physical address for the first instruction. So I'm going to actually fetch the instruction in this physical memory location. Okay, so this is how I'm going to map the logical address into the physical address. Now, let's take a look at another one. So if I continue to execute, and next instruction I'm going to execute is in memory address 0001. So again, it's in the same page. So this is still in the same page. And the offset is 01, so it's a 01. So maps to 000101, right? It's continuous. Okay. Now, suppose I continue to execute. After I execute this instruction in this memory address, so okay, so these are all in the same page. These four addresses are in the same page, so it's going to be in the same frame. So this offset is going to be the same. This is 1, offset is 1, 1. And then the next instruction is located in 00100. And then we find out the page number has been changed, right? It's not in 000 anymore. It's actually in page 1. So then I need to look at the page table, say, okay, here's the page table 1. Where's this page number maps to? It maps to frame number 0011. Okay, so it's 0011. So that's actually frame number 3, right? Okay, now what is the offset? Offset is 00. So I keep copy the offset. So now you actually see the order of the instruction, right? So let me change the color of the pen so you can see the kind of difference here. So if I actually execute the instruction in this logical address, the first instruction, the second instruction in this address, third instruction in this address, fourth instruction in this address, and the fifth instruction is here. So I actually execute the instruction in this order. Now, then I find out each of the instruction in these logical memory location, and which actually corresponding to the physical address location here. So the CPU will actually fetch the instruction in this physical location. Okay, so that's the first instruction location for the first instruction, location for the second instruction, third instruction, fourth instruction. And then I find out the fifth instruction is actually in here. So that's first I find out this page maps to here. Okay, so that's the fifth instruction. And if the next one is this, 6, and that's the sixth instruction. So you see that when you actually fetch the instructions, the CPU gonna actually fetch the instruction in the right location. So here, 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 and here, here. So you don't have to actually put all these instructions in the same physical location. It could be distributed all over the place. Now, if I continue, 7, 8, and 7, 8, and suddenly, in the next instruction, that's the 9th instruction, it's actually in another page, right? So this page, 010, maps to 0010. Okay, 00. This one maps to 0010. Okay, 0010. So then the offset is 0, 0 for the 9. So it's a 0, 0, 1, 0. Offset is 0, 0. So that's 9. Okay. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is actually the actual order of execution. Even though in logically, you can actually follow this order, but in physical location, it does not always follow the same order. It's actually depend on. So now this jump is bigger. Suppose I actually, the previous instruction is in here, and the next instruction is in over here. So in the logical address, they are actually neighbor, but in the physical address, they are really far away, right? Because this one is located in frame number 15. It's at the bottom of the physical memory location. Okay. So that's basically how you're going to actually do the address translation from logical address to the physical address. Okay. So if you look at the text, say if the address is 00010, and then I find out, oh, the page number is 000, and then that page number maps to frame number 0001, right? 0001. So the corresponding physical address is 0001, and then I copy the offset. Okay. Offset is relative location of the address in a page. Okay. So that's basically the idea of paging. So now this diagram gave you some kind of idea. See, here's a logical address. The first part is the page number. The second part is the offset. Now, then the page number, based on the page number, I look at the page table. This page P maps to the frame number F. So I know P maps to F. So the physical address actually must be located in the frame number F. So here's the frame number. And then I copy the offset. Okay. So the relative location of the address doesn't change. Okay. If the offset is 000 in this page, and then the corresponding offset is still going to be 000 in the frame. So the relative location never changes. Okay. It's just like if you interpret a page as a school bus. Okay. So then the offset is basically represent the row of the seats in the school bus. So if you're sitting in the first floor, first row, and then you're sitting in the second row, and then you're gonna say, okay, so you're sitting in the first row. That's the offset. That relative location never changes. And then if someone asks, say, if John is actually sitting in the school bus in the first row, and if I ask, where's John? And you're gonna say, well, I don't know, but I know John is sitting in the first row. That's not enough, because that's only just tells that in the school bus, John is the first row, but I don't know where is the school bus. So then I need to figure out where is school bus parked. If you think about it, if the school bus is actually parked in the school, then the location is the physical address. Then you're going to say, okay, John is in the school bus 7, parked in the school, and he's actually in the first row. So the first row is the offset we're talking about. Okay. So the mapping between logical address and the physical address is pretty straightforward, right? So based on logical address, we figure out what's the page number. And then we look at the page table, find the corresponding frame number. And then we just form the physical address by the frame number plus the offset. So you basically copy the offset. That's the corresponding physical page. Okay. Now let's take a look at another example. That's the last example I want to talk about. Let's say, what is the corresponding physical address for this logical address? Can you tell me? What's the page number? So that's a page number, right? Page number is 3. It's a page 3. Okay. So the page 3 is mapped to frame number 15. Okay. So the page is actually mapped to frame number 15, which is 1111. Now, what is the corresponding physical address? I look at the offset. It's 02. So in the frame, the offset is still not changed. It's still the same. That means it's a second address in this physical frame, because it's a second address in this page. Okay, it's a second in this page, so it should be the second in this frame. So that's a physical address 0001001.
Professor,
Yes.
sorry to ask, but I think I missed something. How exactly do you get 15 from the logical address on the left?
Okay, that's because it just map the page table actually. Here's the thing. In this particular example, the page 3 is actually mapped in frame number 15.
So it's only because we assigned it beforehand that we know?
That's right.
Okay.
That's right.
There's no real way to know unless we already know beforehand, is what I'm understanding.
That's right. That's right.
Okay.
So basically, here's the deal. Suppose I have a program, which is actually organized in this logical address scheme, right? And then the program has, say, seven pages. So then what we do is the operating system memory management are going to check, okay, you have 7 pages or 8 pages for the program. And then I check the physical memory and I happen to find out frame number 1 is available. So basically I load the page 0 into frame number 1 and I record the page table, say page number 0 is mapped to frame number 1. And then for page number 1, I just find the frame number 3 is available. So I load the page number 1 into frame number 3. Now that loading is actually doesn't have to be the same, because this time when I try to run this program, I load the page number 0 to frame number 1. Then next time when I run the same program, it may not be loaded into the same frame. Could be different frame. Depend on which frame is available. Then I can load it. So that's the real beauty of this page.
Okay, thank you. Actually, one more question. Because you said that the actual paging is built into the memory or the RAM, you could say. Does that mean that when manufacturers make chips for memory, do they all have to follow the same standard so that?
If they want to build a memory that support the paging, they should actually tell the customer, say, here's the structure of the physical memory. Now, basically, the size of the page is actually becomes larger and larger because physical memories becomes larger and larger, right? So each page actually becomes larger and larger, So yeah, it's determined by, because that's the best way to do this, because you only need to build this paging scheme into the physical memory, then you can actually gain the performance advantage. Yeah, you can always use the page using the software to build that page, but the software is always slower. So basically, the paging typically requires the physical, the support of the physical memory. Now, how you decide the size of the page is dependent on your physical memory. I think in early computer system, because the physical memory size is very small, so the paging size should be set up very small. But later on, right now, the page is actually, the physical memory size is big, like a 4 gigabytes, 16 gigabytes. So you have to increase the page size. Okay. Now, actually, sometimes you will find out with the modern computer system, using the pages still, even the paging is not really efficient. So they basically build like a couple of layers of page, you know. So instead of divide the physical memory space into like the frame part and the offset part, they actually divide it into like an offset and then frame 1, frame 2. So they actually build, that's called the so then we have to do the something to the mapping, like a page of the page, the table of table of pages instead of table of the frame. So that's, so because the physical memory is actually bigger and bigger, so it just causes a lot of challenging to organize the physical memory. But with paging, it's basically, you know, determined by the physical memory. If the physical memory supports the paging. Now, with the paging, then so it's actually more efficient in terms of the memory management than this consecutive memory allocation. So in that, in which we have to allocate the big chunk of memory space for the whole program. Now with paging, we don't have to do this. We just could chop the program into small pieces of same size, and then we just throw each piece into the frame as far as we have enough frame. Okay. However, with the paging, we still have some kind of a loss of memory space. Now, how this actually happens? This is called internal fragmentation. Okay. Now let's take a look at this. Suppose this is actually the size of the program. This is my code, executable code. So it just consists of a whole bunch of instructions, and each instructions are actually located in the logical address. Now, suppose I try to divide this program into pages, right? So I can say, okay, you know, this is page 0, page 1, page 2, page 3, page 4, and then I have small number of instructions. And if I allocate another page, page 5, now page 5 is bigger than the remaining code. So, but I still need to actually allocate the page 5 for that space, right? Because page is supposed to be the building block for the memory management if we use the paging. So in that scenario, so page 0 consists of all these memory location, logical memory. Page 1 consists of all this. Page 2 consists of all this, and page 3, page 4, and they're all the same size. So I apologize. When I draw this, it looks like a different size, but it's 0, 1, 2, 3, 4. They are all same size. And also page 5. And the page 5, because the program size is from here to here, so there's still actually some space over here that's are not assigned. And these are called internal fragmentation. Okay. Now remember, when we use the page size it's always like use the power of 2 because of the binary, you know, in natural. So when the computer system always use the binary numbers. So the page size is always like a 4, 8, 16, 32, 64, 128. So it looks like we always increase the page size in terms of the power of 2. However, the program size may not be always the multiple of the page size. So it could be the program size could be like you know 0 each of the memory logical memory address, and the last one is 133. So 133 is not really a perfect one. If I have say 128, so then I say, oh, this is good size. The program size, program takes 128 memory space, and the 128 I can perfectly fit into 5 pages. Okay, but if it's 133, so it's actually more than 5 pages, but smaller than 6 pages. So there's still actually a small hole over here. That's called internal fragmentation. Okay. So that's because the size of the program is generally not exactly multiple of page size. Okay. And that some space remains unused at the end of the last page. Okay. At the end of the last page. So that's the last page. So this memory space is unused. Okay. So that's called internal fragmentation. Internal fragmentation is the loss of unused memory space due to the mismatch between the page size and the size of the program. Okay. Now, this problem is, to me, it's not really that big of a problem compared with the like a 50% rule for the consecutive memory allocation, right? So for the consecutive memory allocation, we're going to lose like a 1/3 of the memory space. But here, it's only the last page. And if there's a mismatch, so the last page may not be fully occupied. So that's called internal fragmentation. Okay. Um, so so paging is a very good approach, but there in computer operating system, people actually come out with another memory allocation scheme. That's called a segmentation. Now, paging is kind of good. It's widely used. However, there's a problem with the paging. There's a problem with the paging. Okay. Now, what's the problem? Let me actually take a look at the example. Okay. Suppose I'm going to write a Java program. Okay. So let's say I start the Java program. These are sequential. And then suddenly, so some of the instruction, I want to do the loop. Okay. Or I want to use the if statement. So if something happens, then I'm going to do this. And if something else happens, I'm gonna do this. Okay. So now for this program, you have like a branch, right? You're not gonna always follow the certain order in the execution. Here's the branch. If at this particular location, if the condition is like this, I'm gonna continue to execute the next instruction. If something else happens, I'm gonna skip these block, right? And I'm gonna jump to the else. So there's actually some branch here. So in the code, so when I actually compile this, So I'm gonna actually eventually compile into a piece of, into some kind of instructions. And here's the instruction. Okay. And if I continue, now the if statement, if something happens, I'm going to continue. If something else happens, then I'm going to do something else, right? So now when I load this into the memory, I use paging. So I just cut this. I'm going to cut this. I'm going to cut this. So then it's possible that the sum of the if statement is actually here, and then the else is actually located in another page, right? So if statement is in one page, else is in another page, and it end in another page. So this whole if branch basically going to actually distribute it in 3 page location. But in the logical address, they are still in the consecutive logical addresses, right? So that's page, say, that's page 0, that's page 1, page 2, page 3. But when I load it into the physical memory address, there's no guarantee, because page 1, page 0 could be here, and page 1 could be here. So that means the if statement is actually located here. And the page 2 could be back here. And the page 3 is in the middle. So if something happens, I'm gonna execute, and suddenly I'm gonna jump to here, continue, and then jump to here. Okay. That's, well, from memory utilization problem, that's good, because even though, as far as we have enough frame to accommodate this program, then I can still run this program, even though these frames are located in multiple places. But this can actually have some kind of performance cost, because during the execution, the CPU gonna actually fetch the instruction. But when CPU fetch the instruction, and then CPU gonna fetch the instruction over here, and suddenly jump to here, and suddenly jump to here. So that's a lot of change, because the CPU, the computer operating system, this operating system need to figure out, oh, what's the next memory physical location. It's not always in the consecutive location. It could be like 100 miles away, in a different memory location. So that's one thing. And also, logically, these if statement, the whole piece actually belongs to one piece, right? So it should be always good to actually put them together. Even when we load this, pages into physical memory, hopefully we should load all these 3 pages together, because logically they belongs to the same part, same module. But we have to separate this. Okay. So that's the drawback of the paging. Now I can tell you one example. It's not really a perfect example, but it just give you some kind of idea what the paging gonna look like. Okay. So suppose I have a moving company. And the company gonna actually divide their moving truck, the 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 moving truck, into a component of the same size. I can say that's a page, okay, or a frame. So I can divide my whole truck into 4 frames or 5 frames. Each frame has the same size. Okay. And then when I come to when I try to move some of the family and move some of the furnitures, And then we find out the some of the furniture is really big. It's bigger than the compartment, the frame size. So then what I'm going to do is, well, I have to put all this furniture into these frames. So I'm going to actually cut each of the furniture into the pieces that exactly fit into the frame, right? So I have to cut the furnitures. So I chop the furnitures into pieces and I put through each pieces into each of the frame. And then I'm moving to the destination. And then on the destination, I just take each of the furniture pieces out of the frame and I put them together, right? Now that's not right, not exactly the good good example, but you can see this is really inconvenient. Now in a moving company example, this is not acceptable. So when I actually moving my table, they say, oh, I cannot fit the table into the frame, so I have to cut the table into two pieces, put one piece in one frame, put the other piece in another frame, and then I can assemble later. I'm not going to accept this solution, right? Because my table is just one piece of furniture, so I cannot separate them. So that's the kind of example. So when I try to illustrate the paging, so in this particular example, the if statement is just one piece of furniture. I should really I don't want them to be separated because it's gonna perform. The performance is gonna suffer in the physical memory. So then the segmentation comes to play, and the segmentation basically will look at the original program. Okay, it will logically partition the program. Say, here's the main program, so I should actually put all the main program in one piece. Here's my data. Here's the function I want to call, so I want to put the function in the same location. So they're going to logically partition the program. So here's the example. So I have a program. Okay, instead of like using paging, so I'm gonna say in the paging, I'm gonna put all the code, like this code, data, and the stack, all in one location. So then I chop it. So here's this one into page 0, this one into page 1, this is page 2, this is page 3. So in this case, if I chop using the paging, so and this is page 1, page 2, and then this one of the page gonna actually contains part of the code, part of the data, right? So part of the code, part of data. So this is not right. So I use the segmentation. So I just say, okay, logically, this program contains 3 parts. One is the code, one is the data, the other one is a stack. Okay. And then when I allocate the physical memory, I allocate the code into one physical location. I allocate data in another physical location and a stack in another location. So these 3 segments could be distributed all over the places, but I should not separate the code. Same thing with the program too. Code, data. So the data is actually located here, code is located here. But I'm not going to cut the data into pieces and each piece is going to locate it in the page and put in the different memory location. Okay. That's called a segmentation, which is not the same as the paging, right? So now in order to do this, we need to actually know which segment. So this is segment 0, segment 1, segment 2. Okay. So segment 0 is located in this memory location. So in order to actually record this, I need to keep a table also need to keep the table, just like a page table, but it's called a segment table. Okay, so for each program, I create a segment table, just like the page. So for each program, I create a page table. For each another program, I create another page table. Basically map the pages to the frame number. But the segment table basically match each of the fragment with the physical fragment location. Okay, that's called the segmentation. I'm not going to actually talk about this in much of the detail, but just talk about this in concept. So now for the paging, I can map the page number to the frame number. Okay, that's it. Because I know the page size, all the pages are of the same size, and all the frames are also of the same size. And the page size and the frame size are the same. So I just need to map the page to the frame. And I know which frame gonna start from which memory location because the page size is fixed and the frame size is fixed. But segmentation is not. Okay. So that's why I actually need two data. Okay, for each segment, I actually need two values. Okay, one of the value is called a limit. Limit basically measures the segment size. Okay, limit measures the segment size. And the base basically just tells what is the memory location, what's the starting memory location for that segment in the physical memory. That's the base. It's a starting address of this segment in the physical memory location. Okay, so now in concept, I can tell you this. So suppose I have this program. So I have, for example, main program is here. That's one segment, and I call it segment 2. And there's one function called sqrt. That's a square root function. The main function may call the square root function, but I don't want, because that's one piece of function I implement. I don't want to separate this piece. So I put another segment for this square root. And this is another subroutine, another method. I put this in segment 0. And that here's a stack, segment 3, and a symbol table, segment 4. So the whole program is divided into 5 segments. Segment 0, 1, 2, 3, 4. Okay. Now when I allocate the memory, I need to allocate each of the segment. Instead of allocate the whole program, I allocate each of segment. Okay. Now here's the segment table for this program. Okay. So what I do is for segment 0, which is the subroutine, the size of the subroutine is 1000. That's the size. Okay. The address is 1400. So that means the segment 0 is located in the memory address 1400. Now, how much memory space is going to take? It's going to take 1000 because that's the size of the subroutine. So based on the starting memory address and the size, can I determine what's the end memory address? So start from 1400. The size is 1000. So the last memory address for this subroutine is 1400 plus the size, which is 2400. So that's a lower bound, and that's the upper bound, right? So that's basically defines the memory range. So I actually in the segment table I need two data: the address, the starting point in the memory space, and also size of the subroutine, size of this segment. Now, segment 1, I actually locate, I map the segment 1 into the memory location 6300. So here's a 6300. And the size of the segment 1 is 400. So segment 1 is 400. That's the size. So starting from 63,000, and then the size is 400. So 6300 plus 400, 6300 plus 400, that's 6700. So that's the memory range for this segment 1. And the segment 2, the size is also 400, and it starts from 4300. So it's a 4300 plus 400, so that's 4700. Okay, that's segment 2. So, and segment 4 and this segment 3 and the segment 4 are basically the same. So this is actually, that's the size, that's the starting address, that's the size, that's the starting address. So the segment in the segment table, unlike the paging table, unlike the page table, because pages are all the same, the segment has a various different size. So in the segment table, I have to specify the size of this segment, and also the starting point in the physical memory. Okay. Does that make sense? I think that's pretty much all I want to talk about. So if you read the Zai book, okay, so I'm going to skip these topics. So that means in the test, I'm not going to actually cover these material. One is the segmentation with paging. So they combine the paging and the segmentation into one scheme because they want to take advantage of the good part, you know, good of the paging and the good of the segmentation together. So combine these two. So that's the segmentation with paging, and also with mapping the logical address in the segment space segmentation to the physical memory. It's a little bit more complicated because unlike paging, because paging is so simple because you just divide it, you just chop the physical memory into the same size, okay, and the logical address also into page of the same size. So you just threw each of page into the frame. That's so simple, right? The drawback is they don't actually take a consideration of the logical, the internal logic of the program. So sometimes, one of the block, like a particular while loop, a for loop, this loop should be in the same physical location to 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 boost the performance. But in paging, they could chop it off into and allocate it in completely two different physical locations. So the for loop are gonna actually, if I run the for loop, I sometimes gonna jump between the physical memory location to fetch the instruction instead of actually in the memory space that the nearby. So that's the drawback for the paging. But the paging concept is really simple, so it's widely used. Okay. So I think that's pretty much all for the paging. Okay. Um, so the test on Thursday gonna only cover up to that point. So everything we're gonna talk about after this will not be covered in the test on Thursday. So the next topic we're gonna talk about is the uh, something called demand paging. Okay. I don't think I have time to start this topic, but that's the It's called a virtual memory, and in particular, we're gonna actually talk about the demand paging. You know, so the virtual memory is the collection of one or more logical address space, each of which may exceed the size of physical memory. So far, we talk about the logical memory and the physical memory, and normally we assume the logical memory should be smaller than the physical memory, right? Because typically, the logical memory basically represent the size of the program. When you write the program, so we organize all the instruction of the program into each of the memory, which is actually, before we actually allocate the instruction into the physical memory, the memory address for each instruction is called a logical address. So the first instruction for the program is always located in the logical address 0000000, right? But when we actually load the program into the physical memory, so that logical address 000 may not be 000 anymore in the physical memory. It could be anywhere in the physical memory. But in general, we always assume that physical memory is always larger than the logical memory. That makes sense because when you actually run a program, we have to make sure the program should not exceed the physical memory, right? Because remember, when we try to run the program, we have to load the program into the physical memory. Now, if the program is bigger than physical memory space, then you cannot load the program into the physical memory space, right? Even though regardless which approach you use paging or use something else, because if the logical memory space is bigger than physical memory space, that means you have more bits to represent the logical address than the bits for the physical memory address. So you have more pages than the frames can accommodate. However, using the virtual memory, we allow the logical address space to be bigger than the physical address space. Okay, and we can still run this program. How are you going to do this? We basically use the demand paging. The idea for demand paging is that we don't always load all the pages into the physical memory. Even though the program contains 100 pages and the physical memory only contains 64 frames, 100 pages loaded into physical 64 frames, that's not possible. But initially we only load 10 pages into the physical location and execute this 10 page. And then some of the pages actually complete the execution, so we can actually free up the space and load some more pages. So we can actually, just like a warehouse, so we actually, if we manage these things well, we can actually run a program which is bigger than the physical memory can accommodate. Okay, I think that's all for today. Well, so before we call it a day, I'm gonna ask whether you have any questions. Okay, let me stop the recording.